Okay, in this video, I'll be explaining the variation of potential energy, kinetic energy, and the total or mechanical energy of a body in simple harmonic motion. And these energies, how do they vary with the phase angle, theta? So that's what I'm looking at in this video. And recall that the equation of a body in simple harmonic motion in terms of its acceleration is given by minus omega squared multiplied by the displacement x, negative, showing that the direction of displacement is opposite to the direction of acceleration. And then we also know that the solutions to this equation can either be displacement x is equal to the amplitude x naught cos, I can say, into omega t plus initial phase angle phi. Of course, this initial phase angle comes in when you maybe probably you start timing at a different reference point other than the actual reference point. Okay, just like we have an oscillating body, a simple pendulum. Let's say that this is the maximum displacement, this point A here. I'm supposed to start oscillating at time t is equal to 0. That's at point A. But if I choose to start from any other time, I took my time t is equal to 0 at a point such as P. It means that there's an initial displacement here, angular displacement, which I call my initial phase angle phi. Okay, so that's how we have this in this equation. But if you always start our timing at the exact reference point or position, then we can take our file as 0. Okay, so this is the angular velocity or frequency in radian per second, and this is the displacement. And this amplitude has the same unit as the displacement. Okay, another equation that can be used as a solution to this equation is x is equal to x naught sine into omega t plus phi. Just as I explained the first one, the same thing applies to the second. And you can see that a cosine graph is usually drawn like this. Its maximum is at theta is equal to 0. All right, it has its maximum value here. But for a sine graph, it starts from the origin. Its maximum is, around 90 degrees to above 2 radian, and it varies, as you can see, with angular displacement theta. Okay, so one of these equations can be taken to be the solution of this simple harmonic motion equation. All right, so we're going to see that I want to make use of this first equation and the kinetic energy. Let me start with the potential energy. The potential energy of a body in simple harmonic motion, of course, is given by 1 half kx squared. And this k is equal to m multiplied by omega squared. Of course, I proved that in my previous video. I showed all this. So if you have not are joining me for the first time, I will say I make reference to my previous video lessons to understand all I've done before. Okay, so you can see that now. Now this, if I make substitution here, I'm going to have this, multiply by my x squared and come back to the first equation I wrote here. So I'm going to replace that. That gives me potential energy is this multiplied by x naught cos into omega t plus my initial phase. Now I'm going to square this so that squaring everything gives me half m omega squared x naught squared cos squared into omega t plus phi. Of course, this is square of cosine. Cos squared, whatever it is here, the same thing as finding the cosine and then squaring the result. All right, so that shows clearly that the potential energy of this body varies as the square of the cosine of the phase angle. Okay, so you can also note here that this expression here represents the total energy of a mechanical system. So I can replace this with E naught. E naught represents my total energy cos squared omega t plus phi. Okay, so how do we draw the graph to show the variation? I know that if this is squared, it means that the value of the potential energy will not be positive because squaring a negative number will always give a positive number, all right? Okay, so quickly, if I just have a sketch, a graph of how this potential energy, PE, how does it vary with the phase angle, and that is my theta. Okay, I can quickly label this as mark the theta This is, I can write it in degrees or in radian. So I can write this as 0, 90. 90 is in as pi over 2 radian. I can mark this point as my 180 degrees or pi radian. This is my 270 degrees or 3 pi over 2 radian. And this is my 360 degrees or 2 pi radian. And this is my energy axis. So I can call this my E naught, which is my maximum energy. Okay, so when theta is 0, of course, you know that cos 0 is 1. That reduces expression to E naught, so I mark here. All right, and when theta is 90 degrees or pi over 2, cos 90, of course, you know is 0. So I'm going to mark this point. And when it is 180, cos 180 is minus 1. Squaring minus 1 because of this square, that gives me plus 1. And plus 1 times E naught gives me E naught. So I come here, I trace that against this point and I plot that. 270 is 0, so I mark here. And cos 360 is 1, so 1 times E naught will still give me E naught. So the graph goes like this. Okay, the graph of the cosine function, how it varies with time. Okay, quickly, let's see how kinetic energy, how does it vary with the angular displacement. Okay, that's phase angle. So I'm going to have mv squared and come back to this equation. X equals x naught cos omega t plus my initial phase. Now I have to differentiate this. Sometimes you write it this way. X, I'll place a dot to mean that we are looking for the derivative of the displacement with respect to time. So if I differentiate, because this is a constant term, so differentiating a constant term gives you 0. So it's like differentiating x naught cos omega t with respect to this time t. That will give me x naught or negative, because if you differentiate a cosine, it is negative sign. This one moves in here, and I repeat this as sine omega t plus phi. So that what it gives me differentiating x. So this x dot is same thing as the speed of velocity. That's linear velocity of the body in simple harmonic motion. That gives you minus x naught omega sine into omega t plus my initial phase phi. Alright, so come back here, or let me just square this since I have this square in this equation for kinetic energy. So I'm going to square that. It gives me v squared is equal to x naught squared and omega squared sine squared into omega t plus phi. So when I make substitution in the above equation for kinetic energy, I have 1 half m. I can bring this force omega squared x naught squared sine squared into omega t plus phi. So you can see clearly that this expression here is also the total energy, that is a mechanical energy of the system. So you can see that kinetic energy is a function of the sine squared of the argument, that is this phase angle. So it's a function of the square of the sine. And just as we did for cosine squared, you know that when you square negative and whatever it is, a sine of that angle, it gives you positive. The same thing applies here. So I can have, let's say, 0, 90 degrees or pi over 2 radian, 180 pi radian, 270 degrees or 3 pi over 2 and 360. So I have my sine of that angle. This is 0, 1, 0 minus 1 and 0. So squaring that sine squared, if I call everything here theta, sine squared theta gives me 0, 1, 0, 1, 0. So I want to sketch the same graph or draw the same graph on this same axis that I used to plot the variation of my potential energy with the angular displacement. So I have here when theta is 0, this is also 0, so that starts here. When it is 90, my distance also in this one is same times my E naught, because E naught times 1 will give me E naught. So where I have one, I can put my maximum of total energy, because substitute 1 here gives you E naught times 1, which is still your E naught. So I mark this point for 90 degrees. For 180, that is 0. I mark this point, I plot that point. For 270, that is 1, which is my E naught. Mark this, 360 gives me this. So this graph goes like this. The variation of the kinetic energy with the angular displacement. Alright, so this is how the energy varies. Now the total energy of the system, which is my mechanical energy, Of course, you know, is the sum of its potential energy and kinetic energy. When I do the summation, these two, I have my E naught, that is for potential energy or kinetic energy here, sine squared into omega t plus this my initial phase angle plus my PE had E naught, cos squared into omega t plus my phi. I'm going to factor out E naught, which will give me sine squared omega t plus phi, plus cos squared omega t plus phi. And from trig identity, I'm sure you understand that the sine squared of an argument plus the cosine squared of the same argument is equal to 1. So this reduces to 1, so that my total energy is same thing as E naught. And what was my E naught again? 1 half m omega squared x naught squared, which also depends on the square of the amplitude. So which means the way that total energy vary, that total energy will not even vary with the phase angle. It's constant, so it is independent of the phase angle because the energy value, the line rather, the energy graph is parallel to the angle theta axis. Okay, so you can see that it does not even vary with angle theta. It depends solely on the amplitude of oscillation if the mass is kept constant and the angular frequency is also kept constant. So that's all for this video lesson. The next lesson will take some questions on this simple harmonic motion. Thank you.